Waves in strings, question 4, part A. Below is the frequency spectrum for a violin string. If the string length is 0.45 meters, use the fundamental frequency to calculate the speed of the wave. Well, the fundamental frequency is this one at 0.2 kilohertz or 200 hertz, and at the fundamental frequency there is one loop of half a wavelength, so if that one loop is 0.45 of a meter long, it means the wavelength lambda will be 0.9 of a meter. The datasheet tells us that wave speed equals frequency times wavelength, which is the frequency of 0.2 kilohertz or 200 hertz times the wavelength of 0.9 of a meter, giving a wave speed of 180 meters per second. Part B. If the string only vibrates with the fundamental frequency, show how the displacement of the center of the string varies with time, for 2 marks. We're given a grid with displacement on the y-axis and time in the x-axis, but no units. Firstly, if we find the time period, which is given by 1 over the frequency, or 1 over 200 hertz in this case, so the time period, the time to do one complete oscillation, is 5 milliseconds. We could do with showing a few oscillations, so I've gone for a scale in milliseconds going up to 10 milliseconds. That will give us 2 complete oscillations. The displacement, well, from the wave spectrum previously, it showed a displacement for the fundamental frequency of up to 3 millimeters. It will therefore also go down to -3 millimeters. It's much easier to draw a wave if you mark on a few relevant points to start with. So starting here at 0, we know that at 5 milliseconds we'll be back to this point, so at 2.5 milliseconds we'll also be at the center point. At 1.25 milliseconds we have a peak, and 3.75 milliseconds a trough. 6.25 milliseconds another peak, 7.5 milliseconds will be on the center line, 8.75 milliseconds a trough, and 10 milliseconds back to the start point. It's then easy to add the line. Part C. State 2 factors that affect the frequency of the note and explain the effect in each case, for 2 marks. Well, the data sheet gives us the equation that the fundamental frequency f is given by 1 over 2L the length times the square root of tension T over mass per unit length of the string mu. It's easy now to pick off any 2 of the 3 possible factors. We could increase the length, increasing this term here, would decrease the frequency. We could increase the tension, which is up here, so increasing the tension would increase the frequency. Or we could increase the mass per unit length, which is down here, and therefore would decrease the frequency. We could give a little bit more detail in that frequency is directly proportional to 1 over the length. Frequency is directly proportional to the square root of the tension, and frequency is directly proportional to 1 over the square root of the mass per unit length. Part D. Draw a diagram of the wave emitting only the 3rd harmonic below. Show the magnitude of the amplitude of the wave on the diagram. Well, the 3rd harmonic is the wave with 3 loops in it. And looking back at the frequency spectrum, the 3rd harmonic has an amplitude of 1 millimeter. So I've indicated that on the diagram. Don't forget amplitude is from the center line to maximum displacement.